Hi, today I want to model an inverted pendulum, and I'm going to do it in three parts. The first part, I'm modeling the pendulum, I'm modeling the parts, and then we'll move to the motion application to set up a motion simulation. And at the end, I will control the pendulum or inverted pendulum with MATLAB. So let's just start with making the master assembly. Be careful with namings. The part namings are going to be variables in MATLAB. So MATLAB doesn't accept some characters for variables, so be careful with that. Now if I move to part navigator, I see the pendulum as the master assembly and it is selected as the work part because the font is bold. Now I can move to assembly and start adding new components. The first component I want to have here is the wheel. So I double click on the part that I just made under pendulum and go to home and I start sketching. The sketch plane and the dimensions are not important for now. This is just an example. But later you can come back and change the parameters as you wish. So the real sketch is ready and I can extrude it. Here I click on finish sketch and click on extrude. And I want it to be wide enough so it won't fall sideways, but you can use two or more wheels instead of doing this. So the wheel part is ready. I can now go back to the master assembly, and if I now save, it will ask me for the second name because I didn't name it at the beginning. So I save the wheel part, and the master assembly is now selected as the work part, and now I can add new components. If you don't go back and select the master assembly, the new component will go under the wheel, for example, which you don't want. The next part is going to be the main body of the inverted pendulum. Double click on the new part, go to home, and start sketching. I start sketching on the same plane because it's just easier. Here I keep some distance to the wheel and I need to add some constraint. I want this point to be on this circle and the other point is okay. Click finish and zoom out. Now I can extrude the main body. But I just want to select the regions that I need. So I go back to selection, I deselect all and make sure that the filter is set on region boundary curves and select the curves that you want to extrude. The extrude is the same size as the wheel, but doesn't need to be. You can select anything you want. And as I said, you can always go back to the sketch here and change the size of the body or other parts that you want, or add new parts or remove parts. And if I save now, the NX is asking me for the second name, which is the body. So it's now ready and I can move on to the motion app. But before we go there, I want to change the color of the parts so it's just easier to distinguish. So I paint the wheel brown and also the body maybe with another color so it's just easier to see. Let's go with blue. and this is how it looks like. So before I forget, we also need a ground to check the controller or verify the motion. So before I move, I have to add another part, which will be the ground. So I go to assemblies, new component, add another model, double click, and start sketching. I select the same plane, and I'm gonna have a ground maybe with a slope like this. Here I can offset this. I can offset this line with, let's say, 20 or 100 to the other side. Click OK, and then I close the caps. I'm just making this ready for extrude. So this is the profile of the ground I want to use. Click Finish and extrude. Ground should be bigger than the pendulum, so we're sure that we have enough space. Let's make it 1000. So we have enough space for the pendulum to move around. Now we need to move them to initial condition that we want to import to the motion application. Let me hide everything except the solid body so we have a better view. For example, the wheel should be on top of the ground before we move into the motion, and we should position it the way we want it to be positioned in time 0. So moving here to the wheel, first I need to add some constraint, or I can just select them and move them, but it's easier to constrain them together. Here in the assembly, you can go to assembly constraint. I'm going to use this concentric and keep these two circles concentric, and then I use touch the way that this face touches the ground face. So I can center the pendulum on the ground. So I go with the center 2 by 2. I want to put these two faces in center of these two faces, and now it's centered. So now we have the inverted pendulum model, and it is correctly placed. So I can move to the second part, which is modeling this in a motion simulation. I move to application and I click on motion. Here you need to add a new simulation and name it as you like. It will ask you if you want to component-based simulation, which means that you want to bring in your assembly from the modeling application. If you don't select this, you have to model everything again under this geometry tab. You can start joint wizard. It will automatically import the joints based on the constraint you did in the assembly. I don't have much constraint, so I don't need to check that. And here I can start making the simulation. Before we move on, I need to change this solver. The solver is now on SimCenter 3D Motion, which is actually a good motion simulator, but the connection to MATLAB Simulink is limited. So I move to Recordine, and now you see that the options available are a little bit different. So I move on to adding parts to motion bodies. Motion bodies are basically objects. Everything can be a motion body. For example, the ground is a motion body, and I want to fix it so it doesn't move around, and I name it GR as the ground. Click apply. The next motion body is the body of the robot. You can add multiple parts to the motion body. So if the body had a head part, you could select both of them and they would act as a rigid body. I name it body. I don't need to fix it. Click apply. And the last motion body we have here is the wheel. Now on the motion navigator, you see three bodies and one joint. The three bodies are the bodies, motion bodies that we have in the simulation, and we only have one joint, which is a fixed joint, fixing the ground to the space. If you open the joint, you see that all joints have two parts, action and base. If you leave the base untouched, then the action is fixed to the space. I could, for example, fix ground to something else like a wall as the base, but it's not needed here. Then the next joint that I need is my joint here. It's a revolute joint because I don't want to have axial motion. The only movement possible here is the rotational movement. And you have action and base. Basically, the action should be the part that moves more. I'm just guessing that the wheel is moving more than the body, so I select the wheel as the action. I go here and select between 2 points. I want the origin to be in the middle of these 2 points. That's why the location is on 50%, and you can see on the screen that this point in the middle is now selected. And for the vector, I'm going to use this face to represent the vector. Now you see it in orange, which shows the direction of axis of rotation. And I want the base to be this motion body. You don't need to select anything else for the base unless you click snap motion bodies. This option will, as the name implies, snaps the action to the right place the way that the origins are together. For example, if the wheel wasn't here, it was placed somewhere else, but at the beginning of simulation you want it to be here. So you click on a snap motion body, you set the origin, match the origin of the action body, and the vector matching the vector of the motion body. And then when you start the simulation, the wheel will jump to the location you specified, and then the simulation starts. And let's name this joint motor because we want to drive this joint. We can add some friction to the joint to make it more realistic, and we can also drive it or have a motor here, but I'm going to use another option to drive this. Next, I want to define the contact between the motion bodies. So I use 3D contact, and here you can choose bodies. Remember, these are not motion bodies, so you will select a face inside a motion body. So the whole motion body won't be in contact, but only the face that you are selecting or the solids that you're selecting. And then you need to set these parameters, and you need to make sure that the contact is stable and will converge, because contact has its own algorithm and it goes inside its own loop, and if it doesn't converge, you're gonna have problem in the whole simulation. Here I want to have soft contact. To have more information about the stiffness and other parameters of the material, you can refer to this guideline for contact material in NX document. Here I'm using rubber to rubber, so it's kind of a soft contact that I'm expecting. So and usually you don't need to change other options. I also want to have friction. I may increase the frictions both for dynamic and static to have more friction. We can also define contact between the body and the ground, even though it's not supposed to fall, but it's better for visualization. And now I can have the first run. But before you run any simulation, you have to add a solution to your simulation. There are different types that you can use. The most important ones are normal run and flexible body. Here I'm using normal one, and also I'm using controlled dynamics. If this one is grayed out for you, you need to go back because it is grayed out by default. You need to go back to the environment and then open this up and select motor drive and also code simulation if you want to run a code simulation with Simulink. Also need dynamics. If you select kinematics, you won't have any force involved in your simulation. You will only receive the motions and movements. But dynamic, you get the forces and also kinematics included in your simulation. Here I click OK, then I can go to the solution and select the control dynamics. 5 seconds seems enough. I want a more smooth simulation. This step, you can think of a step as resolution of your simulation. Then make sure the direction of gravity is correct. By default, NX is setting the direction to the z-axis. So if you have another direction set in your model, make sure the gravity is correct. Here is downward and it is as a 1. The other parameters are usually good for any simulation, so you don't need to change anything here. Click OK and I solve the first simulation. To see the result, you can go to the result tab and click play. So here you see we have contact. The movement is as somehow it is as expected, but it seems too bouncy. So to have a quick look, you can go closer, and if you look here, the problem seems to be with the initial penetration. It happens in the first, yeah, here. Here we have too much penetration. The contact calculation is a bit complicated. I have another lecture on this. But basically the software is using this penetration depth to calculate the force, contact force, which is pushing the objects outside of each other. So here we have a lot of penetration, and the software is calculating the penetration force or contact force based on the stiffness, and that generates a lot of force which pushes this part out too much that it starts to fly. Now there are a lot of parameters involved in contact, and sometimes it gets complicated to solve the problem, but the best place to start with is this contact troubleshooting for Recordine, which you can also find on the document of the NX. So it has provided some good solutions that you can start. Here, as I said, my problem is with the initial penetration. I just need to change these maximum penetrations to manual. Basically, Recordine has two types of algorithms to solve contact. It's global and local. It has two types because sometimes global takes less time, so software won't switch the local penetration. And sometimes when the model is big or heavy, that makes a problem. So I just move it to manual and click OK. And just to set the same thing for the other contact, I can copy parameters and paste it there. And just to show you how heavy is this part, if you double click on it, you see how heavy is your part. So I have like 300 kilograms here, and that makes a very heavy contact. So it makes sense if it bounces without setting the parameters. Now I can go back and solve again and see if that helps with the contact. So it seems more reasonable now, and the other bouncing is normal. If I take a closer look here, I think I still have some bouncing at the beginning, but this is normal before the contact converges. Now I want to drive the wheel, and also add a couple of sensors to the body of the inverted pendulum. So I'm gonna use it later for control. But first, driving the wheel, as I showed before, here on the joint you can use the driver tab to drive any joint, and it gives you a lot of options. But these options, for example, driving it directly with a polynomial function, these options are going to be specific to that joint. However, a better solution is to use this driver option. So by defining a driver, it's going to be available to be applied to any joint. For example, now I select this joint, I have the same options. And later on, I can add this driver to another joint. So here I drive it with some velocities. Let's put it on RPM. Let's say 100 RPM. And just to see what is the direction and if everything is okay, I'm gonna scale this up. This is just a display scale, so that's the way it shows on the screen. So this brown pin thing is the joint, and this shows the direction. Since this is not the forward, I want to uh, turn this back to the other direction. So positive velocity is along the direction of the slope. And the direction of driver is going to follow the vector of the joint. The vector is this way now. I just need to reverse direction of the vector and click OK. Now you can see the positive driving speed or displacement is as I like. Of course, there is no difference. I could just use negative velocity here. Under the velocity, I could use a negative 100 RPM, and it would do what I like. But it's better this way. It keeps everything more simple. And I can bring down the scale a little bit. So now it's going to turn with 100 rounds per minute. Let's run the simulation and see the result. So as you can see, it's turning. The friction is not bad. The body is too heavy compared to the wheel. This is 300 kilogram. One option, of course, is to make this lighter with material or remove some material so it behaves better. But this is as we expect. So it moves, the wheel moves forward, and since on the motor joint we define action and base, it's not action only. We could define a joint without a base, but it is action with base. The motor or the drive is also going to follow that and hold to the base while turning the wheel. So that's why it makes the body fall faster. So as the wheel turns forward, it pushes the body backward as well. But we could apply a velocity or torque only to the wheel without holding to the body. That may not be possible in practice, but in theory it is possible, and you can define it here. Now to control this later, I need a couple of information. I need to read a couple of information from the body of the robot. To do that, we need to add sensors. Sensors are returning displacement, velocities, acceleration, and forces. And you can read all directions and orientations for each option, and you can read absolute, relative, or relative to something that is user defined. But to define a sensor or to attach a sensor, you need a point. So before defining a sensor, you need to define marker. Markers are basically points on objects. So here I select this motion body as object, which is the body of the pendulum. And then I need to specify a point. Make it simple. I'm gonna pick a point on the top. Here, gonna go with between 2 points. So between these 2 points, so it's on the center. And also make sure that the coordinate system is as you want, because the sensor, the data that the sensor is returning is going to follow this coordinate system. I click OK, or maybe I'm gonna make this scale a little bit bigger so it's more visible and easier to see everything. So this is my coordinate system for the sensor. Now I can define a sensor. Note that here I also have a smart point. Smart point is exactly like a marker, but you can put it anywhere you want. So a smart point doesn't need to be on an object. You can put it anywhere on a space. So I go back to sensors, and here I select the marker I just made. Now I can extract any information from this marker, which is attached to this body. I need a couple of information. I'm trying to define an IMU, so I need acceleration along all directions. For the X, I'm gonna call it X acceleration, and then Y. And since I don't have a frame of reference, I'm just going to use absolute. But you could have it relative to the ground, for example. If the ground or something else is moving, that would be more useful. And the Z acceleration. And also I want to have the rotation along the x-axis, which is the rotation of the body along this axis. I'm again going with the absolute. So here I need to select the sensor, rotation along x-axis, absolute, and this is going to be x rotation. And okay, so I have the sensors, and then I need to also read the torque on the joint. Now I define a new sensor, I select the motor, it gives me this option of selecting force. It says force, but you can of course select torques. So I'm going to select torque along x-axis, which is the direction of rotation. Let's go ahead and motor torque. Now I have all this data to output to MATLAB, and I want to input the rotational velocity of the motor. So I need to define some inputs and outputs to connect it to MATLAB. To do that, here from the menu, I can go to Insert, Plant, define a plant input, which is going to be motor velocity or voltage or whatever we are going to send from Simulink to NX. And also I need to output all this information from the sensors to the Simulink. Go with the output, brings all these that I want. For each one, I need to define a new output name. This object exists, so I'm going to just double underline it. And we have all the inputs and outputs. but we are getting the input from Simulink, but this is not connected anywhere. To connect this motor input or plant input to the motor joint, I need to first define a function. So I go to the function manager. Here I click new function, write the name for the function, and here in the formula we can't write anything in the function. And if you click apply, it will make a function. Here you get an error that the dimensions don't match. NX is using this thing that checking the dimension on both sides of a conditional if operation. It doesn't make any sense, so you have to change that first. If you go to the file, preferences, and motion, here it has mass function unit policy. You have to put it on ignore units. So when it compares the stuff, compares numbers, it compares 1 to 1, not 1 millimeter to 1 meter or something else. It will return only numbers. And now I can go to the driver and use this function to drive it. So I'm connecting this input with a function to this driver, which is driving the joint. I select function. Here from the function manager, I make a new function. And in the formula, I can use this plant input and the input that I already made, the motor velocity. You can check the syntax by clicking on this check mark. Click OK. I have the signal 1. And now signal 1 is going to be the velocity that is driving the drive 1, which is driving the joint. So click OK. And now the motor velocity input, which is being dictated by Simulink, is going to be the velocity of the joint. Before you start a code simulation, you need to set up the path of the Simulink you have inside NX. To do that, you move to Files, Utilities, and under Customer Default, here you move on to Simulation, Motion, and under Analysis, you go to Recordine tab, and then set the path to the MATLAB under Windows. So here, let me show that you have actually two MATLAB files. That's three MATLAB files actually. One of them is here on the bin. This file is not going to work because it is going to run one of the main MATLAB files under 64 or 32-bit. So what you need to do, if you have, if your Windows is 64 bits, you move to the 64 folder here as the Simulink executable. Then click OK, and now you need to restart your NX for it to take effect. Now, because I have planned inputs and outputs in the simulation, if I click on the solve, it's not going to solve the simulation, but it will ask for a co-simulation setup, which there are two. You can use these NX as a host program. This way, it will run MATLAB from NX, and I will wait for MATLAB to send commands. Or you can use Simulink as the host program, which is easier and most stable one. So here I'm going to use Simulink as a host program. If you click on apply and go back to the same folder that you are doing the modeling, you will now see two files that are just made. If I sort them by modified date, these two files are just made now by NX. The first file is setting the conditions. If I open this one, it is setting some conditions like how many sensors or how many inputs and outputs I have, what are the names of them, what is the time step is being dictated by Simulink, and other options that are needed to set the communication between Simulink and NX. The second file is actually what we need, and it is first running the first file to set the conditions, then it runs the NX client. So to set parameters, as you can see here, to initialize the plan, I need to remove this comment and then run this from MATLAB. Here it starts the MATLAB Simulink and NX communication and waits for information from NX. Now it gives you this NX motion plan block, and make sure that it says client here. If you run NX as a host, this block is going to have host region here. So everything is okay. Also, I can double click here and see details, which is as I expect. I only have a motor velocity and I receive a couple of accelerations and other stuff from the sensors. So I go back, and now you can use this to control the pendulum that we have here. Don't need that window anymore, and everything is going to be controlled from here. So next, you don't need to actually touch this control system that is made in Simulink or the Simulink file. You have to make a new blank model in Simulink. I only use this file, and you can close this because it's just a template that we are using and we don't need it anymore. So now I have this control block here, which is connected to NX, of course. To test, I'm just going to add a constant and try running the motor. So I'm going to send a, let's say, 500 command to the motor, and I'm going to read all the information. I have 5 outputs, so going to connect all the outputs to the sensor, and later we can check this scope to information we have in MATLAB. The time is going to be set from here. I'm going to have it for 5 seconds. I remember that the model from Simulink is going to read files in the folder, the PRT files and simulation files in the folder. It has no direct communication to NX. So remember, you have to save every time you make a change. If you don't save, it's going to read the folder and your files are unchanged, and it's going to read the old files. So every change you make on NX, save here and then go back and run your model. So now the Simulink model is running, and it will show you some messages if the simulation is successful. You also, on the result on the left side, you're going to have a result file after it's finished. So on the status, I can see that it's running. Simulation is solved successfully. It just started to run the time steps. And now the simulation is done. I can now go back to the result and run it. So now you can see this looks like actually 500. It's a lot faster. And if I go back here to my scope, I can see all the information that is being sent from the NX. So next step is to make a control loop to balance the Segway or inverted pendulum.
Okay, in this video, I'm going to show you when you make the NX model for the inverted pendulum or for the Segway, how can you proceed in Simulink to finish the simulation? Already I have the NX model open. So this is the model we have in NX. And if you have noticed, we have a couple of M files and in the same folder that you have this NX model. And if you open this M file that has plant.m, so I think already Hamid also explained what you should do that, but I can repeat that here. You uncomment the last line, and then when you run this M file, it will make a model in Simulink from the NX model. So it's a block, and then you can open a new Simulink file and then just drag this block to the other Simulink file and use it for simulation or designing the controller. So already I have done that. I can open the Simulink file I have, and this one is basically the model we got from the library here. Okay, what do we have here? It's a model with 6 outputs and 1 input. What are the outputs? The outputs we have, they are acceleration along different directions, AX, AY, AZ. We did that. We send these outputs to Simulink to be able to simulate what we have in reality, because the IMU sensor is giving you these 3 accelerations. And also we are outputting here we are outputting omega x, and omega x is basically, if you look at here, x is this direction and omega x is the angular velocity around x. So basically it would be the angular velocity of the inverted pendulum. If you integrate that, you can measure the theta angle. So okay, we have it here, and this omega x is basically what you get from the gyro, and later you can integrate that, and integration in Simulink would be just a simple 1/s, and then of course you need to change the unit from radian. Okay, if you're interested to have it in degrees, you can change the unit from radians to degrees, and then here you'll get the angle of pendulum here, the angle of pendulum in degrees. And also one of the outputs from the NX is theta. So we are also sending the angle itself to Simulink, just for the sake of comparison, to see how good the IMU sensors are working. Let's say we have these 2 acceleration, and if you divide that, and then inside this you have this tangent inverse of the ratio of 2 accelerations. Basically it should give you the angle in radian, and then later you can change it to degrees. But the problem is that one of the problems we had is that the acceleration, when we get the acceleration here in Simulink, is very noisy. So we are working on that to reduce this acceleration, but this is actually due to some of these numerical solution of the NX. So for example, okay, we need actually to investigate that more, but for example, because the wheel is not completely a circle, so it has some corners, it could be because of that and some other reason. So Hamid has done some improvement in the NX model. It used to be more, but it is still there. When I simulate it, I will show you that we have noise here. But in case the pendulum is standing still, in case it doesn't have any displacement, then this angle is perfect, and you can easily see how good you can estimate the angle of pendulum using the accelerations. Anyway, here I'm trying to estimate or to measure the angle of pendulum. So I have used what I have from theta. I'm sending out by theta as the angle. So here I don't bother to actually use the IMU in Simulink because I said that the acceleration is still having some issues. But I assume that we have the angle. And by the way, for example, what we get from here, from the angular velocity, when you integrate that, it doesn't have any bias and it doesn't have any drift. So you can also use this. So what you get here from the angular velocity and then integration is exactly the same as what you get here. But if you use this line, and later you can, for example, manually add some bias to the sensor and see how it works. But for now, because the focus, I just wanted to show you how to work with the model in Simulink. I just used what we get from NX directly, the angle. So, okay, this is about the sensor part. And the next part is that the input we send to the NX is the angular velocity of the motor shaft. So it is basically omega, and what we call it omega m. So NX doesn't have the motor model. It could have, but for some reasons, we actually decided to model the motor in Simulink. And if it is the case, which we have considered that here, then we need to model the motor using these transfer functions and block diagram. If you remember from the course, when I modeled the DC motor, the model of the DC motor from armature voltage. So this is the armature voltage. This is the voltage we send to the armature. I can name it VM, VA. So what you send to the motor as the voltage, it will be, this back EMF voltage will be subtracted from that, and then it goes to the electrical model of the armature circuit, which basically it gives you the armature current, and then you multiply that by the gain, by the torque coefficient, and finally it gives you the torque of the motor. So the output of this block here is the motor torque. So I can call it Tm. If you don't remember, just follow the lecture I gave about this modeling the DC motor. So here we have the motor torque, and then there would be a load torque, which means that whatever load we have connected to the motor, how we model that, it will actually, this torque, the load torque, will be subtracted from the motor torque. And later, this is actually the model of the mechanical part of the motor, the shaft. And it would be also another first order system. And finally, it gives you the angular velocity. The numbers, these values I have used here, just some random values because this, we have changed the size of the pendulum a couple of times and also the weight. So I didn't actually look into that, what motor we should select and what torque, for example, we need and what motor we should select, but you should do that. You know, because in NX model, you can actually decide what is the weight, what is the dimension of the pendulum. And when you do that, basically you can decide what motor you are going to use. And when you have the motor type, you can go to the data sheet and you can find these parameters, and basically you're going to have the model of the motor. So basically, as I said, the block diagram would be the same, but the parameters are of course related to the motor you select. But as I said, this gives you an idea how to model the DC motor if we assume that we are using a DC motor. If it is a stepper, that would be another story. But if we are using a DC motor, that would be the way we should model that. So, and here another output from the NX model is actually the torque applied to the motor. So we have sent that out by the NX model to the Simulink because we wanted to use it here in the in the model of the motor, as I said, we have basically in the model, we have a place to consider the load torque. So this comes here, and I have put a gain here in case the unit is not actually what you want here. So you need to fix the unit, then you can actually use a gain. But if the unit is okay, then you can use it directly here. Okay, so that's what we have. So here now we have the armature voltage that we apply, and then we see how we can control that. So how we do that, for now, don't consider these blocks, only this control loop. So as I said, we have the angle of pendulum here in the feedback. And what is the set point for the pendulum angle? It is always 0. Because of that, I haven't connected anything here, but if you like, I can just type a constant here, and this reference or set point for the angle of pendulum is always 0. So this is the desired value for theta if theta is the angle of pendulum. Okay, so it is always 0. And we can use a PID controller, but later you will see that basically you don't need an integral term here. A PD would be enough. You can use a PD controller to control the system. So I can select the value here. Let me select a high value for P. It depends, of course, on the parameters of the motor, but for now I select a P controller, and I show you how or where to check that. Before I do the simulation, you know that this is the angular velocity of the motor, as I said. If you integrate that, what you get here is the angle of the motor shaft. I have named that alpha m, even though in the course, in the lecture, we had that theta m in the control course, but because we have used theta for the angle of pendulum, I use alpha for the angle of shaft. So alpha m is showing the shaft, the angle of motor shaft, and then you need to multiply that by the radius of the wheel in order to get the displacement of the Segway. So there is another weight here. So what we have here, it is the radius of the wheel, or let's say if it is, for example, 10 centimeters. So let's say we put 0.1 here. And what we get here is the displacement of the wheel. Okay. So now I'm ready to do the simulation. So I have some recommendations for you before you do the simulation. First of all, for some reason, I don't know if it is my computer, because my computer is quite slow, or it would happen for everyone, that when you run this Simulink file that is using a block from NX, it crashes so often. I found some tricks how to minimize the number of crashes. And one of them is that before you run the simulation, make sure there is no scope open. So because when you run the simulation, you open the scopes to see what the result is, and then you change the parameters, and then you rerun the simulation. But when you want to rerun, you don't, maybe you don't pay attention that you have already some scopes open. It increases the chance of crashing. So I recommend you to close all the scopes before you do the simulation. So there's no scope open now. I run the simulation. And when you run, first a text file will appear that shows that the simulation is running successfully or is connected successfully. We can look at that, what the message is. Yes. Yeah, the co-simulation has been solved successfully. And this one actually shows that the Simulink has started to run. So don't stop Simulink. And even when it finishes the simulation, I recommend you just give it 1 or 2 seconds and then open the scope, because you need actually to let the CPU settle down. It happened that the simulation has finished, and then I opened the scope suddenly or immediately, and then it crashes. So give it couple of seconds, 1-2 seconds, and then open the scope. But what the scope to open? So this is what we have here is the theta of the angle of pendulum. If you open that, it seems that actually it is okay. It is controlling the angle of pendulum. And let's see what we have here. Also, it shows that the displacement is okay. You can actually go to the NX and see what happens. You see that it is controlling, even though it is shaking, but still it is controlling, and it is drifting to one side. It was also visible here because the set point for the displacement, if we say that it is 0, it drifts to one side, but it is still okay because it is balancing the pendulum. You can change the parameters of the controller and see how it improves or how actually it will make it worse. Let's give a high gain to the controller, apply, okay. Before I run the simulation, I make sure there is no scope open. Okay, nothing is open. And now I run the simulation. You should wait until you get the text file, and then after you get the text file, Simulink start to simulate the model. Okay, now this is the text file, and if you look at here, it has started to simulate. Don't open any scope in this phase. It will crash the simulation. So now it is finished. I gave it a couple of seconds. I can now open the angle. If you notice here, the angle theta is actually higher than what it was in the previous one. And if you open the displacement, you see it has actually drifted to a high degree. What it means, you can go back to the NX simulation and see, you see, when you increase the gain, it is actually very oscillatory. So it's actually obvious that the controller is not well tuned. Okay, I haven't used the D term yet. It was just a P controller, but you can add the D term and see what happens. Okay, and I can tell you from what I have seen last year's from the student projects, this behavior is quite similar to what happens in reality. So at some point they are able to control the balance, but it is like that. It is shaking too much and it is drifting to one side. Okay. So the next thing I wanted to say is that you will see how you design a controller for the inverted pendulum, but I can briefly explain that here. Other than this main control loop you have to take care of the theta, the angle of pendulum, not to fall over, we would have another control loop. And in the second control loop, if we actually subtract the displacement of the pendulum of the Segway from the desired place or desired position you have for the Segway, and then you use another PD controller. How to design these two PD controllers? Basically, the approach we have is state space approach. So we model the system in the state space and design a controller in that domain. But later you will see that whatever you have designed in the state space, it can be interpreted as two PD controllers, as I have shown here. So there's another PD controller. You can close this loop, and this loop actually will, if it works properly, it will avoid the pendulum to drift. It doesn't let the pendulum drift. That's the first advantage of that. And secondly, if you have a desired position, so let's say what you need is to, if you, for example, to send pendulum 1 meter to the left and then wait there for a couple of seconds, and then 1 meter to the right and wait there for another couple of seconds. So you can easily do that by applying a proper desired signal or a reference here to the second control loop. But the parameters of these two controllers should be designed carefully, because if you don't design it properly, then adding the second control loop will cause the system to become unstable. Okay, so you are adding the second control loop, and you are aiming to not only to decrease the drift, also to be able to control the displacement of the pendulum. But what happens if the design is not okay? The pendulum will fall over immediately. So getting this second loop to work, it could be challenging, but if you have a good model, if you have modeled your system properly, you can do it in simulation, and then you can use this state space controller, and then later you transfer it to these two PD controllers, and then it works properly. Another thing I wanted to say is that to get this second control loop to work, you would need another sensor here to measure the angular velocity or the angle of the motor shaft, which is basically an encoder. So you would need an extra sensor here. Some of the motors, not many of them, but we have some motors that already have encoder, inbuilt encoder. And if you use that, basically at the same time you can measure the angle of the motor shaft. If you don't have it, you can put it externally and then measure that one. So I don't connect it because none of the parameters are actually selected or tuned properly, so I don't connect it. But if you do, you can control it properly. So and again, we may work on this part to improve this, to improve what we get from the acceleration. I can also show you what we have here in the scope. Let's change back the parameters of the controller to the case that it doesn't shake too much. I think it was 3 or something, or maybe even I believe it was less, maybe 1. Just also you could have a D term. It will improve the performance, but for now it's not needed because I wanted to give you the idea. We are not going to design a good controller here. It's just about the idea. So I ran the simulation because I want to show you what we get here. I want to show you how noisy the acceleration signal is. So it has started. Yeah, okay. Now I have given that enough time. I can open this scope. Okay, MATLAB crashed. But here actually what I wanted to show you, I think, yeah, okay. Fortunately, I can do that. So this blue signal is what you get from the accelerators, and then I have filtered that, and this yellow signal is actually the filtered version of the filtered acceleration. And then I have used that algorithm to divide the accelerations and then the tangent inverse. So it works to some extent because this green one is the true value, and the yellow one is what you get after filtering the acceleration. But it is not completely correct. So we are going actually to work on that. And as you know, what you get from the acceleration when the system is shaking, it is not only the gravity acceleration, it is also the acceleration of the system. So you shouldn't also expect what you get from the accelerometers is exactly what you need, because as I mentioned in the IMU lecture I gave, accelerometers are measuring all accelerations or acceleration that the system is applied. So one of them is the gravity. When the system is standing still, the only acceleration that you have is the gravity. But when the system is moving and your motor is applying a force or a torque, then that one also is one of the parameters is being measured by the accelerometers. So because of that, you should expect some noise, but not to this level that you have here. So after filtering that, you see that it helps a lot. So in reality, the IMU sensors, they also have an internal filter, and also when you get the data from the sensors, already they are filtered, but you can add another filter to that if it is not filtered enough. So you can improve the filter. So this is what you have. But I believe that working on this part, it gives you a very good idea. You can, instead of getting the feedback from the true value of theta, you can get the feedback from what you are measuring by the accelerometers. Unfortunately, I cannot do that because MATLAB crashed, but you can do it and you can see how it works. But for now, this part, I'm not actually sure if it is exactly what you get by the accelerometers. Okay. So that was what I wanted to say about the modeling of the system in MATLAB.